All right, so subtracting polynomials, we've been working with these algebra tiles, which frankly were something that wasn't around in my generation, but started appearing after I left school, and students use them now to help make a more visual representation of polynomials and things like what's an x squared, what is an x, what's a constant. And between the what we call symbolic math, which is just the math we're normally used to doing with the numbers and the letters and the x squareds and things like that, and the actual pictures of the tiles, we could do the same thing, one in a very visual manner, one in more of a mathematical manner or a symbolic manner, and get the same answer, but it looks kind of two different ways. It works really well with addition. I find it works pretty well with multiplication and division as well. But subtraction is the one area where it's a little bit more difficult to work with algebra tiles. And to be frank, I think oftentimes it kind of muddies the water even a bit more, maybe confuses the issue. So I'm going to try to explain it to you in a way that it made sense to me. But if you do struggle a little bit with the subtracting of polynomials using tiles, I understand. I think it's probably more difficult than multiplying and dividing. You wouldn't think that's the case, but I think it is. And hopefully we can do it both ways. And I'm going to show you a different way that I like to do it with the tiles as well, which you may want to use for your quizzes in your exam, and it's perfectly acceptable. It's not the way the textbook does it, but I tend to think it works a little better for me. So without further ado, I'm just going to keep going through our notes here. So there's two strategies to subtract polynomials. There's actually way more than two strategies, but those are the ones that we're going to look at. And my pen died. Hold on. Gotta do the normal, take the battery out, shake the pen, put the battery back in, and then hopefully it works again. Just about never fails. And eureka, good to go. So we're going to use algebra tiles, and the way we're going to do it here is we're going to look at the brackets, and the brackets are always very important, as we know, as bed math. So let's just think of these as two sort of different things. Okay, we've got the first set and the second set, and you can see that they're separated with a subtraction sign, with a minus sign, right? So what the book recommends that we do is let's model what's in the first set of brackets, and then we'll worry about the subtraction part later. So if we model just using our drawings of tiles, the first set, we've got 3 of the big blocks positive to represent positive 3x squared, and then we've got negative 4x or minus 4x, and we know that those are the tall, thin rectangles, and because they're negative, we shade them in. Okay? So we don't worry about the colors in this class. What we decided right at the beginning of the unit for the new people is that anything that was filled in is going to be a negative, and anything that's not filled in is going to be a positive. So these big tiles here represent positive x squared tiles, and these ones just represent negative x tiles. And we don't have any constants. Everything's got an x, so if we just had a number, that would be a constant, but we don't have those. So model what's in the first set of brackets. That's what we did. And then the steps after that is dealing with the more difficult part, which is how do we subtract something that's in brackets with a polynomial. So what they're recommending to us here is to subtract the part that's in blue, 2x squared minus 6x. We need to take away, okay? And that's just using words to say subtraction. We are going to take away. We've just got to be very careful about what we're taking away. So if we look up at the blue brackets up here, we need to take away whatever's in the brackets. And what's in the brackets is two terms. We have 2x squared is something we need to take away. And we also have to take away, negative 6x. And this is the part that becomes the problem, is because we're taking away a negative. So what really is going on there is we're subtracting a negative sign, or we're subtracting a negative number. And anybody who's been with me for the entire math class knows that whenever I see two negative signs back to back, I just turn them both into positives, because a negative okay, is a positive. But it's a confusing concept, I think, when we're dealing with algebra tiles. Because how do we draw it? How do we make sure that we're subtracting a negative instead of subtracting a positive because it's going to give us the wrong answer. So the textbook or the recommended approach in our notes here is just to take it one step at a time and take it slowly and think of the negative sign with the word, okay, or the words take away. And I do think this is a good idea because I think that if you remove that negative sign, it kind of removes a little bit of the math anxiety with it. So we're just going to think of that negative sign as take away, and then we have to take away whatever's touching the negative sign. In this case, what's touching the negative sign, okay, if you think about it, is the bracket, okay? The bracket is touching the negative sign. So I have to take away whatever's inside the bracket, which means I can't forget about the second part. It's not just the 2x squared. I have to consider the negative 6x as well. So I'm going to break that into two different parts because there's two terms in this particular polynomial, which we know is called a binomial. We need to take away a positive 2x squared. So that's 2x tiles. We need to take that away. All right, so if we're starting with what we've got here, which is 3x squared minus 4x, okay, I'm just going to draw a quick arrow from here to here to show you it's the same model. I know that there's some stuff going on over here that looks a little different right now, but we'll get to that as part of step 2. So we started with 3 positive x squared tiles in my original drawing, and now we need to take away 2 of them. And that's pretty easy because there are 2 of them to take away. So all I'm doing essentially is circling 2 of those, and then I'm taking them away, which means I'm canceling it out. Okay, so I'm just going to do that. We can get rid of those because I took them away. Now the more difficult part is, if you want to number these, that's sort of step 1, that's step 2. The more difficult part of this is I need to take away 6 negative x tiles. I don't have 6 negative x tiles. I've only got 4. If you look up here, I've only got 4 negative x tiles. So how am I going to remove 6 of them? I can't. So we have to have a different process whereby we get an extra 2 negative x tiles, but we don't actually change what our equation or what our expression means at the end. We can't just be like randomly adding and subtracting things just so that it looks nice. We have to make sure it makes mathematical sense. So this is where the concept of zero pairs comes in. A zero pair is something that looks different but doesn't change the answer. Okay? For instance, if we're talking about, let's say I have the number 2 and I want to turn that into the number 2, but I want to multiply it by something. Okay? I could multiply 2 times 3 over 3. So I actually made it look a little different, but I didn't, but I didn't actually change the answer because 3 over 3, okay, is just 3 divided by 3 is 1, and then 2 times 1 is 2. So I can make it look a little different without actually changing the answer. So we're doing that in a special way here by adding the tiles that we need. So those are the 2 negative x tiles. But we're also going to add 2 positive x tiles. And if you think about it, this really adds up to 0 because I've got -1 plus -1 is -2. So I've got -2, and then I've also got a +2 down here, which cancels out to 0. So all I'm doing by adding these so-called zero pairs is just making it so that my tile model has enough things for me to get rid of. So I just took this entire tile model here, and we tacked it on to the end of what we already had, because we already had 4 negatives at the top. So when I tacked on these tiles, now I find that I have 6 negative x tiles that I can take away. So I circle them all and I get rid of them, or I cross them out, or I do whatever I do. But the 2 positive tiles that I added as part of this zero pair, okay, they stick around because it doesn't tell us anything about taking away positive x tiles. It tells us to take away 6 negative x tiles. And I've already done that. And then just like in addition, at the end of the day, once you've canceled out all the things you need to cancel out or removed all the things you need to remove, you just look at what's left and you write out the answer symbolically. So what do I have left that I haven't crossed out? I've got one positive x squared tile right there, and I have two positive x tiles right there. That's how I get to the answer using tiles. And again, I think the most difficult part about this is understanding how to add the zero pair or pairs, or however many you need, to your model in order to make it so that you have enough tiles to remove for a subtraction question. Okay. So I understand that that's a more probably confusing process than addition, and I will tell you that I think multiplication and division are even easier than this when you're using tile models. So if you understand what I did there, you're probably going to be okay. If it's a little bit vague, you might want to go back and watch this over one more time after, or ask me a question via email, or bring a textbook question to a live session, and I can work with you a little further. But that's the way the textbook recommends doing your tile models, or your pictorial models with the actual algebra tiles when you're doing subtraction. And it's not always that difficult. For instance, if I told you that you had 2x squared, this is a totally separate example. Let's say if you had 2x squared plus x, and then I wanted you to subtract x squared plus x, okay? This wouldn't be nearly as difficult, okay? Because let me just draw it, right? I'm going to draw the first polynomial. There's your 2x squared, and there's your positive x. And what do I need to take away? I need to take away, okay, remember that's the minus sign. I need to take away one positive x squared, and I need to take away one positive x. Now I have both of those already, so it's not a big deal. Here's the positive x that I have to take away. Okay, that's this one. And here's the positive x squared that I have to take. Doesn't matter which one I pick, so I'll pick this one. And then all that's left over is just 1x squared. So that wasn't nearly as difficult because I had what they wanted me to take away already in my original, or the front, polynomial. It just becomes more difficult when you need to take away something that you don't have. For instance, okay, if I needed to take away, just using that same example I just had, if I needed to take away, let's say positive 4x's, now I'm in a situation where I'm going to have to start adding zero pairs because I only started out with 1x. So how am I going to take away 4 of them? I only got 1. So that's an example, again, where you're going to have to start using zero pairs. So that just means a combination of both positive and negative tiles that works out to 0. The example we had up here, 2 negatives and 2 positive x's, that's going to cancel out to 0. So sometimes they're pretty easy. Sometimes you have to add a few tiles, and it does get a little bit more complex. When we're doing this symbolically, and remember, symbolically means just using the normal math symbols that we have here. Whenever you see something of the form, okay, something like this, I'll circle it here so you can see exactly what I'm talking about. Whenever you're subtracting an entire polynomial, the easiest way to do that is to always distribute the negative through the terms in the bracket. I'm having trouble spelling today. Okay, so that is something you just absolutely need to do. I'm just gonna put a little separator in here so that I can show you what's happening down here. Okay, always distribute the negative sign through the terms in the brackets. Now, that's just fancy math talk, but it's something that I'm sure you've seen before, either in your Math 9 class or in 8, 7, maybe in grade 6. I think you might have handled something like this. So distributing means just that you multiply the negative sign through everything that's inside these brackets, which means it's a -1 times the first term, and it's also a -1 times the second term. And that will make it so that you're just adding, okay? And then the signs will work out properly. I always draw those little rounded arrows to remind myself that I have to multiply that negative sign by every term. Otherwise, it's easy to miss one. And remember, there's not always just 2 terms in there or 1 term in the bracket. Sometimes there's 3 or 4 or 5. Okay, so using those arrows helps me keep that straight. All right, now the first step in these, at least the way I do them, is always the same. You just drop the brackets on the first one. You can always just drop the brackets on the first one as long as there's no negative sign out front, and there isn't. So for step number 1 on this question, okay, I would just drop the brackets on the first one, 3x squared positive minus 4x, and then I write out the second part exactly the way as it's written. I'm not going to distribute yet. So that's always my first step, is just remove the brackets from the first polynomial. Okay, so then my second step for these is going to be distribute the negative sign through the terms in the bracket. So I'm going to leave what I had at front because that's not what I'm doing right now. What I'm doing now is I want to do this part here and distribute the negative sign. So what you need to do at this point is you need to just treat this as -1 times whatever's in the brackets. And I always draw the arrow, right? There's an arrow to that term and there's an arrow to that term to remind myself that when I'm done, I should still have 2 terms. The only difference is the sign changes. If you're ever subtracting and you've got a negative sign up against the bracket, not -4 or -5, you've just got a negative sign up against the bracket, all that happens is the sign of each term changes. So you don't have to really do any math or multiplication. You just have to say, well, I had a positive 2x squared in the brackets, so if I distribute that negative sign, now a positive 2x squared becomes a negative 2x squared. And if I had a negative 6x, that's going to become a positive 6x. So as long as it's just a subtraction or just a negative sign in front of the bracket, okay, all you're really doing is just changing the sign of each term in the bracket. So a positive 2x squared is a negative and a negative 6x squared is a positive. And if you keep that in mind and you remember that process, then you're not likely to make mistakes on that in an exam. It's less complicated than thinking about it as multiplication. It's easier just to think of it as change the sign. Now, that doesn't work if you've got like a -4 or a -5 touching the bracket. Then it's a little different, but we're not at those yet. Okay, so now the third step is always collect like terms. So what are we going to collect that's a like term? Well, this is from a unit before. This is from 5.2 or a section before, 5.1 even. No, it's 5.2. That's what it was, like terms. And as you remember, those of you who are with me, I make little signs underneath the terms that are the same. So I just made a little S there, little squiggle under the x squareds, because those are like terms. They're both x squareds. And then maybe I put a little square or something underneath the other like terms, which are the 4x, -4x, and the positive 6x. And the reason I do that is just to make sure that I've dealt with every term and that I didn't try to add something to something else that I shouldn't have. I know I can't add x to 2. I can't add that because x is not the same as 2. They have a different degree. I can't add x squared to x. One's an x squared and one's an x. I can't add or subtract a 1 from x squared. Hey, those are already as simplified as they're going to get because the terms don't match. Okay? So now that I've made it so that I know which terms are like terms, then I just put them back to back. So now I've got 3x squared, okay? And then I go to my other squiggle. And by the way, once I know I've used one of these terms, I usually just put a line through it so I don't accidentally do it twice. Then the next one I've got a squiggle under is a negative 2x squared. So I took care of that one. So I'll put a little squiggle through that one. And then after that, I've got a negative 4x. Okay, that's the first box one, so I'll get rid of that. And then I've got a positive 6x. So then I'll put a squiggle through that. Now I can just look at what I had on the green line and say, okay, I did something with every single one of those terms, so I'm probably going to be okay. And then the last step is the easiest of the steps. You just group whatever you've got left. So I've got a positive 3x squared, and I got to get rid of or take away 2x squared. So it's just subtraction, right? 3 minus 2 is going to leave me with 1x squared. I don't write the 1. We just write x squared. So I have a single x squared left. Okay, so that's these two. Okay. And then if I look at what I've got after that, I've got a negative 4x and a positive 6x. Well, that's just going to be a positive 2x, right? If I start in the negative and then I go 4, I get to 0, and then I've got 2 more, so that takes me to 2x. So that simplifies to that. And I can't take that any further. That's as simplified as it can be because x squared is not a like term with 2x. X squared can only be added or subtracted from other things with x squareds. And the same thing with 2x. Okay? So your final answer is x squared plus 2x. Do you always have to write out all 5 steps of this? No, I don't think you do. I think you can probably do it in 3 steps pretty reasonably. But I always want you to show a little bit of work so I understand what your thought process is. And if you make a mistake, I can help you out. So that's why I always recommend that you write out a few steps. Don't just try to do it in one. Don't just write the answer because I don't know where you got it from. I don't know how it got there. You won't get full marks. You need to show your work for these. But you may be able to skip one of those steps and still be showing me enough work. Okay, so let's go to the official example number 1, and it says use algebra tiles for this subtraction. Okay, so let's go back up, and we're just going to use this model that we did up here. Okay, so we're gonna write number 1. We're going to write out what the first block is. So what's the first block? We've got a negative 2a squared. So I'm going to draw 2 of the bigger squares, and they're negative. So I'm just going to shade them in. So there's my negative. Okay, there's my negative 2a squared plus an a. Okay, so a variable, that's just a positive a. And then minus a 1, so a constant. That's the first time we've seen a constant. So I've got a little square that's shaded in to represent that it's a negative 1. So that's what's in the first polynomial. Now, number 2, I need to take away okay, 1, okay, negative a squared tile. Okay, so I need to take away 1 positive a squared tile. Because now I'm just looking, this is the takeaway part, but what am I taking away? A positive a squared. I need to take away 3, I'm writing it out in words, okay, negative a tiles. Okay, again, you're not going to do this much work when you do it. I'm just trying to go through it step by step, as in the above example, and I have to take away 2 positive constants tiles, or constant tiles, and that's the little squares. Right? So I got to take away 2 of those. So in order to do that, let's draw what we have and see what we need. Okay, so we've already got 2 negative a squared tiles. Excuse me, squares are not quite as square as they should be. Okay. And I've got 1 positive a, and I've got 1 negative number, a constant, so just 1 of them. I need to take away 1 of the positive a squared tiles. I don't have any positive a squared tiles, so I'm going to manufacture those using 0 pairs. So if I want to add an a squared tile, a positive a squared tile, to my equation, if I need to add a positive tile to my equation, I'm changing it. But if I add 1 positive and 1 negative, that's a 0 pair, which means I've changed the way it looks and I've added a couple tiles to this model, but I haven't actually added or changed it in any way. All I've done is drawn these 2 things, which essentially cancel out, so that I have 1 a squared tile to cancel. So I'm going to cancel it. It tells me get rid of 1 a squared tile. So there we go. I got rid of that. Now I need to get rid of, And I'll just put a little green thing here to indicate that this is the step. Okay, this was the red thing I circled. Now I'm going to use green for the second thing here. So I need to get rid of 3 negative A tiles. I do not have 3 negative A tiles. I have 1 positive. I'm just going to double check my math, make sure it was actually 3 negative A tiles. It is. I have 1 positive A tile. And I'm just going to move this guy out of the way just for a second, just so I have room to do what I need to do. So he's still part of this model. I just moved him away a little bit. So in order for me to get rid of 3 negative A tiles, I have to have them first. So I'm going to draw 3 negative A tiles. Remember that a negative A tile is the long rectangular one, but because they're negative, they have to be shaded in. So I'm going to add, or I'm going to bring these tiles into my model. The problem is, once again, I can't just go putting whatever I want into my model without making sure that it cancels out. So I have to make sure that I have enough plus A tiles to cancel out the ones that I added on the bottom. So if you look at these 3 negative tiles, I also added 3 positive tiles, which means I added 0. I just made it look different. Why did I even bother doing that? Because I need to get rid of 3 negative A tiles. Well, here's my 3 negative A tiles. Now those can go away. The last thing I need to do is get rid of 2 positive constants, so 2 positive little squares. Well, once again, I don't have 2 positive little squares, so I'm going to have to change or augment my tile model a little bit to make sure of that. So I'll just make sure you know that that's the blue step that I'm doing here. So if I need 2 positive tiles to cancel, let's draw them in. There's 1 of them, there's 2 of them, but I can't add them into the model without making sure it's a 0 pair and having the negatives to cancel it. So now I have 2 positive constant tiles that I can circle. That's the negatives I circled because my brain's apparently not working so well. So we're supposed to get rid of the negative ones. We're supposed to get rid of the 2 positive ones. So I will get rid of those. And now we just compile or group what's left over in our final answer. So our final answer is going to be, what have we got left over? We've got 3 big rectangles. Don't worry about the colors. The colors aren't important. What's important is it shaded in or not? So I've got 3. And the reason we're not using colors or not caring about colors, for those of you who weren't with us at the beginning of the unit, is because oftentimes you're doing this in pencil and you just have the one gray color. So how are we going to tell what color is negative and what's positive? We're not. Whatever's shaded in is negative. Whatever's not shaded in is positive. We decided that right at the beginning of the unit, so there's no confusion. So I got 3 of those. And then I've got, remember, we're only counting the things that haven't been canceled out. And if you think it makes more sense for you to actually draw a line through these things that you canceled out, that's fine too. What have I got left that's not canceled out for positive A tiles? I've got 1, 2, 3, 4, it looks like. And what have I got for these little squares that represent our constants? It looks like I've got 3 negative ones that aren't crossed out. So I can look at my final tile model and I can say, well, my answer to this is going to be negative 3A squared. Okay. Plus, because we've got positive 4A tiles, and then we've got 3 negative constant tiles. So it's a bit of a process, but as long as you remember to change the minus sign in your head to the words take away, and then you take away each thing in the brackets, including the sign, then you'll at least know what you need to draw with regard to 0 pairs in order to be able to circle, you know, in this case, I needed to circle 1 positive A squared, I needed to circle 3 negative A's, and I needed to circle 2 positive constants, which are the small unshaded squares, and that's how I was able to do it. All right. And for the next example, I don't think I'm not going to draw This one, is it the same question? I'm actually not even sure. I'll just have a look. Is it the same question? I think it is the same question. This time we're going to do it symbolically, which frankly, 90% of the time you'll do it symbolically because it's way quicker and you don't have to draw anything. And it's just the tile model is just a more pictorial view to help you understand what's actually going on behind the numbers. Mohammed, we spend an hour on our math every day. Negative 2a squared plus a. I'm going to go quicker now because I've already explained how to do it. So remember, my first step was just to write out, okay, or to drop the brackets on the first one. Okay, the second step, now I'm going to distribute the negative sign. So I'm not changing anything out front, but I'm going to distribute this negative sign to the three terms inside. So a positive a squared becomes a negative a squared. A negative 3a becomes a positive 3a. And a positive 2 becomes a negative 2. Now I just need to group the like terms. In this case, those are my a squareds. Those are my a's. They're in nice order this time. And those are my constants. So let me just get to the answer. I've got a negative 2a squared minus another a squared, so I get negative 3a squareds in total. I'll cancel that out. I've got a positive a and three more positives a's, so that's 1 plus 3 is 4 a's. Okay, and then I've got a negative 1 and then two more negatives. So I'm negative and I'm getting more negative, which means it's negative 3. Okay, so that is the symbolic way. So I got negative 3a squared plus 4a minus 3. Hopefully that's what we got when we used the tile model. Negative 3a squared plus 4a minus 3. But you notice how much quicker it is, okay, if you understand the steps symbolically and you use that three-step process I showed you. Okay, last one. I'll do this one really quickly, and it's only different because it's got xy tiles, y squared tiles, and x squared tiles. Remember, it doesn't matter how many letters there are in a term. Okay? They have to be the same in order for them to be like terms. So we don't need to change the way we do things at all. We just have to recognize that it's okay that there are different letters used as variables inside of an expression. It's fine. I'm going to use the exact same process. My first step, I'm dropping the brackets at the front because there's no negative sign in front of this first polynomial. Okay, there's no negative outside the brackets. That means I can just drop the brackets. So this is kind of an unnecessary step if you really understand what you're doing. Okay, but I am just doing it, okay, sort of the long way to make sure I do every step very carefully. Okay, now I've got to distribute, right? So I don't change anything out front because nothing needs to be changed yet. Y squared. Okay, now I need to distribute. So I always draw the arrows. That negative needs to go to each term inside the back polynomial. So a positive x squared becomes a negative 8x squared. A negative 7xy becomes a positive 7xy. And a negative 4y squared becomes a positive 4y squared. Now I need to group like terms. This is the only part that maybe is a bit more challenging on this one, but really it isn't, because you can see clearly that's an x squared and that's an x squared. You can also see clearly that's a y squared and that's a y squared. And you can see that that is an xy, and this is also an xy, and that takes care of all of them. So it's really no different than just doing like a 5x squared minus 3x plus 2 kind of type question. There's just a few more letters in it. So let's group them all. Now remember, you always write this from high degree to low degree, right? Highest degree to lowest degree. So we have to deal with the x squareds and the y squareds first because they've got the highest degree. So I usually write them just in alphabetical order. It's a good rule of thumb. So let's just do the x squareds first. So I've got a positive 5x squared, and then I've got to take away 8x squareds, which is going to leave me with negative 3x squareds. I can cross those off because I dealt with them. Then I have to do the y squareds because they've got a higher degree. Okay? So the y squareds, I've got 2y squared, and then I've got a positive 4y squared, so I've got two positives, which means it's going to be plus 6y squared. Cancel those out or cross them out so I don't accidentally add them twice. Then I've got a negative 3xy and a positive 7xy. Well, negative 3 plus 7 is going to give us a positive 4xy. Don't forget the variables. That takes care of this one and this one. None of those things that are left are like terms. An x squared is not the same thing as a y squared. and an xy is not the same thing as either of the front two terms, which means I can't subtract or add anything else to this. It's as simple as I can write it. Okay? Now, we could check the answer just by going back in. And how do you check subtraction? Well, if you think about it just as a, sort of a mental math deal, if you think about it, if I have a very simple question that is 8 minus 6 equals 2, how do I check if the 2 is the correct answer? By using all three numbers. Rhetorical question. Okay, how am I going to check if that's the right number? Let me just reverse it and add it and see if by adding, okay, if I bring this -6 over to the other side and switch it to a positive, does that equal 8? And it does. So that's a quick check. You can do the same thing by plugging in these three things. Just treat this, okay, treat that as the 8, okay, treat the second part as the 6, and treat your answer as the 2. So I always try to make a simple model before I go any further. So what would this look like if I was checking it? Okay, I should probably get rid of those in my final notes copy because I think people might think it was part of the original solving part, which it wasn't. So what I'm going to do here is I'm just going to use this simple model that I created with the 8, the 6, and the 2, and then substitute in the things that I have from the above equation. So what was the first number? In this case, it was the 8, so that's going to correspond with the first thing over here, which is the 5x squared. 5x squared minus 3xy plus 2y squared. Okay, so that's the 8. That took care of this. Then what's on the other side? And I'm putting equal question mark because I'm checking it. I don't know that this is going to work out. So now I have to add the other two things. Well, what is representing the 6? The 6 is being represented by this polynomial right there, which I kind of half erased, but I think that's a -7xy. So 8x squared minus 7xy. So this is 8x squared minus 7xy. And then was it plus x squared or plus y squared? Minus 4y squared. Minus 4y squared. And then, so that's the 6. And then what's going to represent the 2? The answer is going to represent the 2 because it did in our original little checky equation here. So hopefully when I add -3x squared plus 6y squared plus 4xy, hopefully that all works. Okay, I'm going to do it very quickly because I want to spend about 15 minutes with my new students just going over the class website. Okay, so on this side of the equation, remember now we're just checking our answer. This is just checking to see if we got it right. Okay, does this equal question mark? Okay, well I'm just going to drop the brackets. 8x squared minus 7xy minus 4y squared. Excuse me for going quickly. This is plus now, right? This is plus now. You see it right there, which means I could just drop the brackets. So I've got -3x squared plus 6y squared plus 4xy. Okay, now just what are the like terms? Plus 4xy. Okay, now I just got to identify the like terms and add them together. So nothing changes on this side, right? This is what I'm checking to see if I've got it correct. Plus 2y squared, question mark. Okay, so I've got 8x squared minus 3x squared, so that's 5x squared. Okay, I've got a negative, sorry, I've got, they've got the xy's. I'll do the xy's even though I wouldn't typically do that in this order before if I was solving it, when I was solving it. So there's my xy and there's my xy. So I got a -7 plus 4 is going to leave me with -3xy. And then very last thing I've got there is my y squared and another y squared. So I've got -4 and a +6, which is plus 2y squared. So I look, is that equal to that question mark? Yes, it is. Therefore, it is checked. So I always find that just creating yourself a little math equation. Where did I get the 8, the 6, and the 2? I just grabbed them from my head. I just grabbed 3 numbers that are small that made sense to me. So I made a simpler, it's making a simpler model, right? I said, well, instead of dealing with all those x squareds and x's and xy's, let me just make a simple math equation in my head and then see if I can test it. So I said, well, I know 8 minus 6 is 2. So if I was going to test it, I would see if 6 plus 2 is equal to 8. And then I just used the polynomials and subbed them in for, you know, this is in place of the 8, this is in place of the 6, and this is in place of the 2. Okay, so I'm going to move a little bit more quickly tomorrow when I go through multiplying and dividing. I do think that subtraction is probably the hardest of the 4 operations with regard to tiles. Oh, Kenny says he got a different answer. Which one? For which question, Kenny? Did I make a mistake? Very possible I made a mistake. I sometimes do.
So like for the 2, like, wait, hold on. I need to check my answer. Like the question where it's like 2a with like the power of
Oh, way
2.
up higher? This one here?
Yep. Wait. Yeah, I got minus 1a, and then like with the power of 2 minus 2a plus 1.
You got minus. Okay, did you remember to distribute the negative sign here?
Yeah. Yeah.
Okay, so does your first line look like my first line?
Yep.
I'll do it again. I'm happy to do it again. Maybe I did make a mistake. Sometimes it's easier just to start fresh.
Oh, I don't know if I made a mistake though.
Okay. Only one way for us to find out, right? Let's just do it. I'm always glad when students say that. Say I got a different answer, because it's very possible I made a mistake. I'm as prone to them as anybody. So let me just check. I'll do it very quickly. Negative 2a squared plus a minus 1. And then I've got to distribute that negative sign, which means everything inside the brackets needs to change signs. So an a squared becomes a negative a squared. A negative 3a becomes a positive 3a. And a positive 2 becomes a negative 2. Okay, that's an a squared. That's an a squared. That's an a. That's an a. That's a squiggle. That's a squiggle. So negative 2a squared minus a squared is going to be 3 negative a squareds, because I'm negative and I'm getting more negative, right? That takes care of that.
Yep.
I have a positive a and 3 more positive a's, so that should be a positive 4a. And then I have a negative 1, and I'm getting more negative by 2. So if I'm already negative and I'm getting more negative, then I have to be a negative 3. I don't know if that's the answer I had before, but that I'm reasonably confident that that is the right answer.
Okay. Thank you.
Usually if students make mistakes on this, it's distributing that negative sign and forgetting to switch the signs of one of the things in the second polynomial.
Oh, I see.
If you want to email what you got, just take a picture of it and email it to me. I'm happy to look at it and let you know.
Oh, I kind of just scribbled it. It looks kind of messy, so
That's all right. Give it another shot. If you still get an answer that's different than mine, like I said, feel free to email it to me. I'll work with it.